Hi everybody, I'm really excited to present the new family of compressors in the Hertz-Kompressoren line of compressors. The Hertz impetus low horsepower 2-stage variable speed rotary screws. My name is Ed Maxwell and I'm the Northeast Regional Manager for Hertz-Kompressoren US. My presentation today will show how the Hertz 2-stage variable speed compressors save energy, reduce maintenance costs, and perform more efficiently than any single-stage machine. The Hertz products I'm going to focus on in this presentation are the 22 to 75 kilowatt machines, that is 30 horsepower up to 100 horsepower, 2-stage rotary screws. Hertz has 6 offerings in this category: 30, 40, 50, 60, 75, and 100 horsepower, in pressures ranging from 100 to 125 to 150 psi, both air and water cooled, with an optional heat recovery kit. Here's an overview of the global compressed air market expected growth over the next 10 years, with a 5% per year growth expectation. Looking at the 2-stage market, the expectation is for a larger per year growth of 5.6%. I expect this growth to be even more than that because of the tremendous energy savings that 2-stage machines provide, and even more because of the new efficiency requirements by the U.S. Department of Energy. Compressed Air Best Practices published an article on the pros and cons of single-stage and 2-stage rotary screw air compressors back in July of 2020. However, back then, the smallest 2-stage machine was 125 horsepower. And one of the negatives presented in the article for 2-stage machines pointed out that there was a big price differential between 2-stage and single-stage. The new Hertz impetus 2-stage machines have prices that are very close to the single-stage machine, so that objection is now ruled out. Here's a graphic showing your basic single-stage rotary screw with 2 rotors driven by a single shaft, taking the air in at atmospheric and increasing it to the desired outlet pressure, usually 100, 125, or 150 psi. A good analogy for a single-stage air compressor for those of us who live in the north would be like one person pushing a car out of a snowbank. Here's a graphic showing the 2-stage air end. Note the over-under design. Atmospheric air enters the inlet, raising the pressure in stage 1, and then stage 2 increases the pressure to the desired outlet pressure. Sort of like 2 people pushing that car through the snowbank instead of 1. 2 people doing the work instead of 1. 2 people sharing the workload, making it easier for each of them. Yes, our primary purpose when we sell a compressor is to provide the end user with the air required to run their equipment. But the real challenge is for us to show the end user that their biggest long-term expenditure is the cost of the energy to drive that compressor. And this cost of energy has to enter into the equation during the sales presentation. The fact is that in the 10-year life cycle of a typical air compressor, the biggest cost by far is the cost of energy. 75% of the overall cost of ownership is energy. Only 12% is capital equipment, 13% maintenance. This slide shows the standard formula for computing the annual cost of running an air compressor. The kilowatt at full load for any compressor, as well as its motor efficiency, can be found on the KGI website, kgi.org. The utility charge per kilowatt hour has to come from the local utility company or the end user's utility bill. And finally, the hours of usage must come from the owner or service tech servicing the machine or from an energy audit. This spreadsheet is meant to show the end user very quickly, with the machines running 100% of the time in this example, and in this case it's 6,000 hours, what the energy savings would be between a single stage and two-stage machine. In this case, the savings would be $3,803 per year, with a price difference between the single and two-stage machines being approximately $7,500. That means there's a 2-year ROI when you factor in the energy savings in your quote to the end user. This spreadsheet shows that even with a single-stage VSD compared to a two-stage, there's $3,400 per year savings and a little over a 2-year ROI. Note that the price differential between single-stage and two-stage 30 horsepower and up is just about 15%, and after 2 years, the energy savings goes right to the owner's bottom line. In certain parts of the country, utility companies will give energy rebates if you can show that the proposed compressor is an energy savings improvement over a baseline compressor. This spreadsheet shows the baseline 50 horsepower, fixed speed, single stage compressor. We plug in usage based on a load analysis of the customer's usage. We use compressed air challenge formulas in the spreadsheet to show the load profile of a fixed speed machine. This machine would be running load, no load over 6,000 hours per year. Note the annual kilowatt hours of 285,579 in this sample. This computes to a little over 44,000 per year in energy costs. The second sample, the one that we would propose to the utility company for a rebate, is a Hertz two-stage machine with the same load profile as the baseline sample. Note the kilowatt hours in this case of 226,545, 60,000 kilowatt hours less per year than the single stage. Note also that the two-stage machine produces about 5% more air than the single stage. This is a pretty dramatic comparison to show the end user. With a two-stage machine, the energy savings over the 10-year life would be about $90,000, $9,000 per year. And this, of course, goes right to the company's bottom line. We're now going to look at why two-stage machines will reduce long-term wear and tear on the machine and therefore lower long-term maintenance costs and add to the life of the air end. Thrust load is the axial force acting on the compressor shaft, putting stress on the bearings in the shaft. In a single-stage compressor with one shaft, the thrust load is almost 10 psi when you raise the pressure from ambient to 125 psi. In a two-stage machine, the thrust load is shared, decreasing the long-term maintenance costs, increasing the lifetime expectancy of the air end. Note that the thrust load on each shaft is less than half of the thrust load on the single-stage compressor. 3.4 psi in the first stage, 3.98 psi in the second stage, raising the pressure to 125 psi. Finally, we'll look at the efficiency of the two-stage machine compared to single-stage. KGI has developed a formula that shows the isentropic efficiency of machines, which will allow us to compare two machines with different characteristics. The closer a compressor's isentropic efficiency approaches 100%, the better the compressor converts input energy into useful output. Once again, I want to point out that energy is 75% of the total lifetime cost of an air compressor. This graphic shows us how, when you have two workers doing the job gets done better and more efficiently, much the same as a two-stage air compressor. This is the KGI formula used to compute isentropic efficiency from full load operating power. All the variables in this formula can be obtained from the KGI datasheets. I took that formula and converted it into an Excel spreadsheet. Again, I took the data from a KGI datasheet, plugged it into the cells, put in the formulas, and in this case, I computed the isentropic efficiency of a Hertz impetus two-stage 75 horsepower and found the efficiency to be 86%. That is, this machine is converting input air into useful energy with an efficiency of 86%. This is an incredibly high efficiency, and I'll explain why Hertz machines are so efficient in a couple of minutes. I took some KGI data from a competitive compressor manufacturer and plugged it into my spreadsheet. And this is the case of another two-stage machine with a lower efficiency of less than 80%. 10% less than the Hertz machine. I feel it's important to show potential end users this kind of information to help them make informed decisions. This slide summarizes the reasons why one machine would have a better isentropic efficiency over another. First of all, if it runs cooler, it will be more efficient since heat is the enemy of compression. Second, if the design engineers have created a better air path from inlet to outlet, this will result in lower friction loss and more efficiency. Third, using oversized motors and separators contributes to this efficiency. And finally, using permanent magnetic motors, which are the motors of the future because they run cooler with lower electrical loss during operation and a higher production capability. The following slides show the features of the Hertz two-stage machine. This is very important features. Small footprint, high energy efficiency, low operating temperature, all adding up to one of the best and most efficient two-stage machines on the market. Here's the package for the 50 to 100 horsepower design. Note how very open and easy the machine is for maintenance. All machines come with a zero loss tank drain, and all 100 horsepower and less machines have permanent magnetic motors. This slide shows the design of the Hertz 30 and 40 horsepower machines. Same zero loss tank drain, same variable speed fans, same permanent magnetic motors. As I said earlier when discussing isentropic efficiency, airflow is critical to efficiency. This slide shows how the engineers have designed the airflow in the Hertz two-stage machines, which results in reduced pressure loss. The oversized components also have a direct correlation to isentropic efficiency. Here we have the oversized intake system of the 50 to 100 horsepower, which results in incredible sound attenuation. Honestly, you can stand right next to these machines and talk in a normal tone of voice, no matter what the horsepower. The sound attenuation is excellent on these two-stage machines, with the permanent magnetic motors especially. Here's the intake system of the 30 and 40 horsepower. Both systems have large isolated intake chambers with two-stage filtration, 99.9% particulate filtration, and an incredibly low pressure drop. The secret sauce, as I've said earlier, for the Hertz two-stage low horsepower machines is the oil-cooled permanent magnetic motor. Over the years, the PN motor design has improved so much that it's now being used in all the Tesla cars because of its energy efficiency, long life, and larger production capacity. The Hertz small horsepower two-stage machines have oversized SEP and SEP separation systems with an efficient separator using a centrifuge tank. The cooling system for all our low horsepower two-stage machines use variable drive cooling fans, again resulting in a high cooling efficiency and a better isentropic efficiency. All of our low horsepower two-stage models use compact, high efficiency heat exchangers. All of our low horsepower two-stage units use zero loss tank drains and achieve 99% water removal even in humid environments. Finally, our Smarttronic electronic controller has user-friendly touch controls, uses a single inverter for the compressor motor and the fan motors. These controllers can manage up to 4 compressors and offer lead, lag, and weekly scheduling settings. They're very user-friendly. This slide shows part of the 539,000 square foot Hertz factory in Istanbul, Turkey. Hertz also keeps a large inventory of machines in their North Carolina warehouse where modifications are made such as tank mounting, adding integrated dryers, and voltage and pressure modifications. Here's the outside of the building in Istanbul with approximately 500 employees. Dalga-Kirin is the parent company of Hertz, and Hertz-Kompressoren is the premium label of the Dalga-Kirin brand. Smart Parts is the global aftermarket parts program for Hertz. Thank you, and please leave comments below. Definitely contact us for further information and check out our website, hertz-kompressoren.us. Thank you again.